If we are to have an honest conversation about the state of the automotive industry in 2026, we must start by dismantling a lie that has persisted for exactly 140 years. Since the very first internal combustion vehicles rolled out of sheds in Germany, the fundamental interface between the machine and the road has remained primitive. We have been sold the idea of advancement by brands like Mercedes-Benz, Bentley, and Rolls-Royce. They use seductive marketing terms like magic body control or active ride. But if you strip away the leather, the wood, and the soundproofing, and look at the raw mechanical engineering, you find a system that is functionally identical to a Victorian horse-drawn carriage. We rely on a passive system, a steel spring to bear the weight of the vehicle, and a tube filled with oil, the damper, to stop that spring from oscillating indefinitely. This system is, by definition, a compromise built upon a failure. It relies on the principle of reaction. The wheel must first hit an imperfection in the road surface. It must be forced upwards violently, and only then does the damper attempt to mitigate that energy by forcing hydraulic fluid through tiny, restrictive valves. This creates a fundamental physics problem known as hysteresis. No matter how fast the processor in a modern Porsche Panamera is, the oil in the damper has physical viscosity. It takes time to move. It takes time to build pressure. There is a physical lag, a latency, between the road impact and the suspension's reaction. For a century, engineers have gaslighted us. They told us that this lag is unavoidable. They told us that the trade-off between ride comfort and handling precision is an immutable law of physics. They told us you cannot have a car that handles like a Formula One racer and rides like a hovercraft. They lied. The truth is that the solution to this problem was identified decades ago. We must look back to the early 1990s. The Williams Formula One team developed the FW14B, a car with active hydraulic suspension that was so dominant it was banned by the FIA for being too effective. It proved that if you control the ride height actively, you gain massive aerodynamic advantages. Simultaneously, Dr. Amar Bose, the genius behind Bose Audio, spent 30 years and hundreds of millions of dollars proving that electromagnetic motors could replace dampers entirely. His Project Sound, Lexus prototypes could jump over obstacles and corner with zero body roll. But the car industry killed the project. They claimed it was too heavy, too complex, and crucially, it consumed too much power. The giants of Germany and Detroit looked at the future, shrugged, and returned to polishing their antique hydraulic valves. They chose evolution instead of revolution. They bet that the internal combustion engine and the 12-volt electrical system would rule forever. They were wrong. They failed to predict the rise of the high-voltage electric vehicle platform, which would finally provide the immense energy source required to make the impossible D-end suspension a reality. This brings us to the technological rupture we are witnessing today. BYD, a company that began by making mobile phone batteries in Shenzhen, has effectively picked up the baton that Western engineering dropped. With the Yangwang U7 and the Disu Z system, they have mass-produced the linear motor suspension. But we must be surgically precise about what this is. This is not air suspension. Air suspension is just a rubber balloon replacing a steel spring. It is still governed by the slow movement of gas. The Disu-Z eliminates the fluid and the gas entirely. It is a dry system. At each corner of the car, there is a three-phase linear electromagnetic motor. Imagine a high-speed maglev train wrapped into a compact cylinder inside the wheel arch. When you apply electrical current, it generates force, not pressure, but force. And it does so at the speed of light. The critical number that defines this revolution is 10 milliseconds. That is the system's reaction time. To put that in perspective, the human brain takes approximately 200 to 250 milliseconds to process a visual threat. A blink of an eye takes 100 milliseconds. The Disu-Z is reading the road via LiDAR and sensors, calculating the force vector, and physically moving the wheel 20 times faster than you can perceive that a bump exists. This allows for the application of skyhook theory in the real world. The car body remains fixed in space, perfectly level relative to the horizon, while the wheels articulate furiously underneath, mechanically disconnected from the chassis. The motor can extend the wheel into a pothole and retract it before the shockwave has time to transfer to the cabin. It effectively erases the topography of the road. Furthermore, we must address the unsprung mass myth. For decades, critics and purists argued that bolting heavy electric motors to the wheels would ruin handling, as heavy wheels carry too much inertia. This is true for passive systems, but the Dsu Z is active. The motor is powerful enough to manage its own mass. It can accelerate the wheel downwards at speeds greater than gravity, 9.81 tawan mas 2, forcing the tire into the tarmac to generate mechanical grip where none existed. It turns the suspension from a shock absorber into a downforce generator, or it creates a level of connection to the road that no mechanical spring, no matter how expensive or well-tuned, can replicate. If the U7 represents the luxury application of this technology, the Yangwang U9 represents the weaponized application. This car features the Daisus X system, the most extreme iteration of the technology. This is where we see the true potential of the 800-volt silicon carbide architecture. The suspension system on the U9 has a peak power output of 36 kilowatts. Think about that for a second. The suspension alone uses more power than the entire drivetrain of a small city car. Why? Because to defy gravity, you need brute force. The viral footage of the U9 jumping off the ground is not a carnival trick. It is a demonstration of power density. For a 2.5-ton vehicle to leave the Earth, the motors must deploy explosive force instantly. But the real revolution is not the jump, it is the safety capability. The U9 allows for three-wheel drive. In a traditional supercar, a Ferrari, a McLaren, or a Lamborghini, if a wheel disintegrates at 120 mph, the suspension collapses, the chassis grinds the asphalt, the friction causes a violent spin, and the result is often fatal. The U9 is different. Its sensors detect the loss of vertical pressure in milliseconds. The Dsus X system instantly retracts the hub of the missing wheel, lifting it clear of the ground. It then stiffens the diagonally opposite corner to act as a fulcrum and uses the quad-motor powertrain to torque vector the car straight. It turns a catastrophic mechanical failure into a manageable event. This is the ultimate redundancy. It proves that the analog feel of European supercars is actually just a lack of active safety systems. The comparison with European rivals is brutal. The Porsche Panamera uses a 48-volt active anti-roll system. It is good. It can twist a bar to stop roll, but it cannot lift the car. It cannot jump. It cannot drive on three wheels. The 48-volt system is a toy compared to the 800-volt sledgehammer of the Dsus X. BYD has brought a nuclear weapon to a knife fight, and the legacy manufacturers don't even realize they are dead yet.
After digging into Chinese EVs lately, I was genuinely blown away. It's easy to dismiss them based on old stereotypes, but the reality on the ground has shifted so dramatically, it's almost unrecognizable. Once you look under the hood, especially at how they've rethought suspension systems, chassis dynamics, and overall vehicle architecture, it's clear they're operating on another level. This isn't just about catching up. It's about fundamentally rethinking how a car is designed and built from the ground up. If a German or American brand had this kind of engineering breakthrough, they'd be running Super Bowl ads about it, proclaiming a revolution in mobility. The marketing machine would be in overdrive for months. But Chinese companies often just ship it. No hype circus, no grand pronouncements. They seem more interested in building than boasting, letting the product speak for itself. The focus is on tangible progress, not perceived prestige. A big part of why they're moving so fast? Talent. And it's not just homegrown genius, it's a global brain trust. A lot of the designers and engineers behind these cars came straight from Porsche, Mercedes, BMW, you name it. They brought decades of experience in perfecting vehicle dynamics, build quality, and brand prestige. And they were unleashed on the most critical component, the battery. They've pioneered cell-to-pack and even cell-to-chassis designs, eliminating redundant materials to boost energy density and structural rigidity. This makes the cars safer, cheaper to produce, and longer range. They're also leading the charge on new chemistries, from cost-effective LFP and LMFP cells to next-gen sodium-ion batteries that remove cobalt and lithium from the equation entirely. Paired with 800-volt architectures, this means charging speeds that can add hundreds of miles of range in the time it takes to grab a coffee. This speed is enabled by a revolution in manufacturing. We're talking about hyper-automated factories using gigacasting to produce huge sections of the car's frame in a single piece, drastically reducing complexity and cost. With the entire supply chain often located just a few miles away, the feedback loop from design to production is incredibly short. And now they're expanding globally, not just exporting cars, but building assembly plants in Europe, Southeast Asia, and South America. They're actively seeking out the world's toughest safety standards, earning top marks in European NCAP crash tests and building out service networks to support their new customers. The real-world results are undeniable. You get more range and better efficiency than in similarly priced Western models. The software experience, with seamless over-the-air updates and genuinely intuitive interfaces, makes many established luxury brands feel a decade old. The total cost of ownership is simply lower. These are people who got tired of corporate red tape, quarterly profit pressures, and committees killing bold ideas before they even hit the clay model stage. They were frustrated by a culture that prioritized incremental updates over genuine innovation. They moved to China because they're actually allowed to test their wildest concepts. Fail fast, iterate faster. That's the mantra. It's a culture that rewards ambition instead of sanding it down for shareholder comfort. That contrast says a lot. Western legacy brands aren't failing because they lack talent. They're constrained by a system where investors come first and customers come second. A system that fears cannibalizing its own profitable gas-powered history. And here's the irony. Many of those same premium cars are already packed with Chinese-made components. The battery management systems, the infotainment chips, the electric motors themselves. They get assembled in Europe, slapped with a Made in Germany badge, and the price jumps tenfold. It's a masterclass in brand marketing. Then, when something breaks, suddenly it's cheap Chinese parts. The narrative conveniently shifts to blame the supplier, not the brand that specified and integrated it. But when it works flawlessly for years, providing the seamless experience customers paid a premium for. Crickets. The German engineering gets all the credit. It didn't have to be this way. The legacy automakers had every advantage. The brand loyalty, the engineering pedigree, the global footprint. But right now, one side is building the future, while the other is busy protecting the past. And the sheer pace of this innovation is fundamentally reshaping what we should all expect from the cars we drive.